Okay, hello. So I am going to repeat myself a little bit here because this is an extremely important concept that we've talked about, and to understand everything that's going on in electromagnetism, you really need to understand that if you have a magnet and a charge in the vicinity of each other, they exert no forces on each other. The magnetic force and the electric force do not, in a sense, interact. But we said that if the magnet moves relative to the charge, or the charge moves relative to the magnetic field, then each does feel a force from the other. So therefore, the charge acts like a magnet when it moves. And then if the charge moves or the magnet moves, if they move relative to each other, the charge then feels a force, and the charge will change its direction due to the motion of the magnet or the magnetic field or the motion of the charge. So let's say, for example, I've got this fixed charge Q here. It's just floating in space. Let's just say it's not fixed, but it's not moving. And we've got this magnet, and it is also fixed and it's not moving. Let's say that these two are on a surface on the table, and they're not going to be exerting a force on each other. But let's say then I go ahead and I move the magnet. Let's move the magnet just to the right. If I move the magnet to the right, then, so that's just supposed to be a velocity v, the charge will then feel a force. We can go back and we can say, oh, well, if the magnet's moving to the right at speed v, that is the exact same thing as if the charge is moving to the left at speed v. So even though the charge may be stationary and the magnet is moving, it's all relative, and so it's the same as the charge moving to the left at speed v. And then we can understand that the charge feels a force, at least because we've written down F on a moving charge is QV cross B, where the charge is moving through a magnetic field. And so the fact that the charge is moving through the magnetic field, let's just see, for example, let's take the field line through which I show the charge moving. At any point, the charge is going to feel the force. But let's just say that the magnetic field is at that, the magnetic field at that point is in this direction. The magnetic field at that point is in the direction shown. And so V cross B, so the charge will change direction. The charge will feel a force, QV cross B, and the direction of that will be out of the page. Put your fingers in the direction of V, rotate them towards B, your thumb points out of the page, and so the charge will feel a net force out of the page, a magnetic force out of the page. Okay, so the charge feels that force. So what this tells us is that we just said that all motion is relative. So if the magnet moves relative to the charge or the charge moves relative to the magnet, it's still going to feel that force out of the page. So what this tells us is that if the force is stationary and the magnet is moving to the right, the charge will still feel a force out of the page and the charge will start to move. That is Faraday's law of induction, that moving magnets then cause charges to move. A different way of saying that is that moving magnets cause charges to move. A different way of saying that is that moving magnets cause currents, right? Because moving charges are currents, or moving magnets induce currents. And what is a moving magnet? But it's just a changing magnetic field. It's not a stationary magnetic field. It's not a static magnetic field. It's a changing magnetic field. So what Faraday's law of induction says is that changing magnetic fields create forces on stationary charges, makes them move, so it therefore creates currents. I think you were already aware of that, and you were aware that is probably one of the more important, if not most important, discoveries of the last 200 years, or however long ago that was, approximately 200 years. And one of the most impactful things that on our lives, because this is how we generate electricity. We generate electricity by moving magnets near wires, therefore inducing electric currents in those wires. So let's just take a look at what Faraday's law tells us from an equation point of view. What Faraday told us from an equation point of view about how big that current is that's induced. So while moving magnets or changing magnetic fields will exert forces on stationary charges, making them move and creating currents. Typically, all we care about are currents in closed loops, right? I mean, when we did circuits, we saw this idea of a circuit is a closed loop. If you don't have a closed loop, if you simply have a wire, if this is a wire, this brown thing is just a wire that normally we always say that the wire is connected to something, but let's say this is not connected to anything. It's just a straight wire that ends. It's not a long straight wire. And I have a magnetic field that is changing, right? That is changing, dB dt, some kind of changing magnetic field. And by the way, remember that dB dt just means simply that the field is changing with time. Whoops. Okay, try that again. Okay, so I have a magnetic field, B, which is changing with time. So that's not going to induce a current in this wire because the charges have nowhere to go, right? There's a charge in this wire. There's one here, and there's one here, and there's one here, and there's one here, and there's one anywhere you look. But those charges will feel forces, but they're all stuck in the wire. They have nowhere to go. You got to have a closed loop. So in order to induce a charge, in order to induce a current, you've got to have a closed loop. So we have a changing magnetic field in a closed loop of wire. Again, a changing magnetic field will exert forces on free charges in space, but we are typically don't have a whole lot of free charges sitting around that we're watching. Although there are free charges everywhere, what we're interested in is how Faraday's law of induction impacts currents in wires, or charges in wires. So Faraday's law of induction says that changing magnetic fields induce currents in closed loops. So because there's a closed loop, then the magnetic field must have a magnetic flux through that loop, right? So the magnetic flux, remember, phi is the magnetic flux is the integral of B dot dA. So what Faraday recognized is that what was important is about how not just how the field changes, but how the flux changes. Because if the area of the loop gets smaller or larger, that is effectively the same as the magnetic field getting smaller or larger, at least in the sense that, well, certainly the magnetic flux is getting smaller or larger. There's more or less magnetic field going through the loop. Also, Faraday recognized that that if the magnetic field was parallel to the area of the loop. In other words, if the loop is in the plane of the page and the magnetic field is in the plane of the page, and there's no magnetic field going through the loop, that while that magnetic field, if that magnetic field was changing, it would exert forces on the charges. It would not exert forces on the charges in the right direction to induce a current. So there would be no current induced in that loop. The magnetic field has to actually go through the loop. It's kind of hard to draw that in 2 dimensions, I mean. In any case, the picture on the left, this one is meant to imply that the magnetic field is parallel to the area of the loop, and then this picture here sort of shows the magnetic field going through the loop, where you will induce a current in the loop. Okay, so what Faraday recognized is that it was how the flux changed as much as the magnetic field. If the magnetic field changes, the flux changes, but also the angle of the field to the area and also the area itself. So a changing flux induces a current, d flux dt, a changing flux induces a current, or if it changes at a constant rate, remember that's the same as a delta flux over delta t. In other words, flux final minus flux initial over delta t. That's just for if there's no if we don't have to take a derivative. That really just says that the slope of the line is the same everywhere. That's just left over from the concept that dv dt, the acceleration, is equal to delta v over delta t if v changes at a constant rate. That's just a mathematical fact. Okay, getting back to changing flux. So if the flux changes with time, then we induce a current in a loop. If we've induced a current in the loop, then we must have created a potential difference. that pushed those charges to create a current, and we call that potential difference an EMF. We induce an EMF. An EMF is really, we've actually seen that before. It's abbreviated capital epsilon, or EMF. And that's just a potential difference. That's an induced potential difference, or an ideal potential difference for a battery. We've seen that before in the book. We didn't talk about it much. But an EMF is just a potential difference. That's all we care about for now, is that it is a potential difference. So if the flux is changing through a loop, we create a potential difference, or an EMF, that therefore creates a current, right? Remember that potential difference, delta V equals IR, for example, for a resistive element, etc., right? So EMF is the same as delta V. So therefore, if we induce a potential difference, we induce a current, IR, where R is the resistance of the loop. So what Faraday was able to show is that the EMF, or the potential difference that's induced in that loop, is equal to, in magnitude, the time rate of change of flux. So let's explore that a little bit. First of all, recognizing that E equals IR. So it induces a current. I is d phi dt over R, right? So therefore, I equals 1 over R d phi dt, where this is changing magnetic flux. In addition, that's for a single loop. If there are multiple loops, each loop, right? If there's a coil, for example, each loop adds another area A, so we generally write this as if it's the area of a single loop, and therefore that the EMF induced is equal to N d phi dt. So d phi dt is the changing flux through a single loop, and then if we've got a coil with N loops, then the induced EMF in that coil is N d phi dt. And therefore the induced current is N over R d phi dt. So the only other thing we need to understand about this law is that I have an absolute value in here, and so we do need to understand that there is a direction. Even though none of these are vectors, there is a direction associated with this, because the flux can get bigger or smaller, so it can be positive or negative, right? So it's a scalar, positive or negative, and the current can go clockwise or counterclockwise, and it's sort of a pseudo-vector kind of situation. But there is a negative sign, and we'll explain. Then it doesn't really matter that there's a negative sign. This is how we calculate the induced EMF, or the induced voltage. This is how we calculate the induced current. The negative sign tells us about the direction of the induced current. So let's put in the negative sign, and then I'll just say, when you're calculating things, you can ignore it and then figure out the direction of the current later, and that's really what the negative sign is telling us. So this is a summary of Faraday's law, and then I include the sign. The sign is, we put a negative sign between the two, and the sign means, the negative sign, right, that means that what it tells us is that the current induced by the changing magnetic field creates a magnetic field that opposes that which created it. So if the magnetic field, for instance, is pointing in the example in the upper right hand corner, the magnetic field is sort of pointing to the right through this loop, then the current induced in the loop, if that magnetic field is if it's changing in that direction, if it's getting bigger in that direction, if the magnetic field is getting bigger to the right, then it's going to induce a current that points to the left, that opposes the direction of the field which created it. So this is called Lenz's law. Lenz's law. The negative sign, the explanation of the negative sign. It comes in Faraday's law, but the actual fact that the current induced has a magnetic field that opposes that which created it is called Lenz's law. So let's go back to our example again. So if the magnetic field is increasing to the right, in the direction shown, so let's just say dB dt is increasing to the right, then that is going to induce a current, and let's just, it's kind of hard to tell in 3 dimensions, but that's going to induce a current that's going to have a field to the left. So that's going to induce a current that goes into the page, right hand rule, right, thumb to the left, that goes into the page on top and out of the page on the bottom. And so that would induce a magnetic, that current would have a magnetic field that points to the left. Let me try to, points to the left. So the induced field, due to the induced current, points to the left. So I will say that comes out of the page in the bottom and into the page at the top. Okay, trying to draw that in 3 dimensions is a little bit difficult. And the minus sign sort of makes sense, because if the induced current was in the direction such that it enhanced the magnetic field, it would really not account. It would really go against energy conservation, and so it should oppose it. It should try to push back on the change that's creating it.